You know that atoms join together to form molecules, particular arrangements of particular atoms to form particular structures. Those structures make up everything around you, and those molecules determine the physical and chemical properties of, well, everything. But why do atoms do that? What are these chemical bonds, and why are they stable? Are there different kinds? And if there are, how do you know which is which?
Why does stuff even exist?
Before you can understand anything in chemistry, or why molecules have the properties they do, you need to understand the nature of chemical bonding. Why do chemical bonds form? Well, the precise answer depends a little bit on what kind of bonding we're talking about, but they all operate on the same basic principle. Bonds form due to the mutual attraction of atoms. Atoms that are together are lower energy than atoms when they're apart. That means that the formation of chemical bonds is always favorable, downhill. It releases energy. In chemistry, we call changes that release energy exothermic because the energy exits the system. And the reverse must be true. Breaking chemical bonds to separate atoms that are attracted to one another must be unfavorable. It has to be uphill, requires an input of energy. We call that kind of change endothermic. Endo because the energy goes into the system, it gets absorbed. Bond forming, downhill, releases energy, exothermic. Bond breaking, uphill, absorbs energy, endothermic. You're already familiar with one simple classification of chemical bonding. Bonds can be either ionic or covalent. When two atoms combine to form an ionic bond, one atom transfers an electron to the other. So now there's a cation and there's an anion. Those two particles have opposite electric charges, so they're attracted to one another. Each ion is surrounded by multiple ions of the opposite charge in what's called an ionic lattice. This normally occurs when a metallic element loses an electron to form the cation and a non-metallic element gains the electron to form the anion. You already know about orbitals and about atomic properties, so you have a good sense of why this is happening. Metals are on the left side of a row, so they have a relatively low Z effective, high energy valence orbitals, and that means a low ionization energy. It's relatively easy for those elements to lose their electrons. In contrast, nonmetals are on the right side of a row. They have a high Z effective, lower valence electron energies, and so it's more favorable for those elements to gain more electrons. So metals tend to form cations, while nonmetals tend to form anions. But keep this in mind. Transferring the electron is not what is driving the formation of the chemical bond. In fact, moving the electron can sometimes be thermodynamically uphill. The driving force for this bonding is the mutual attraction of the positive and negatively charged ions. Now, when two atoms combine to form a covalent bond, they share the electrons between them. The attraction is still between negative and positive, but rather than the attraction of an anion to a cation, it's the attraction of the shared electrons to the positively charged nuclei. The shared electrons are now interacting with two positively charged nuclei, not just one, so they're going to be lower energy. This type of bonding interaction usually results in a discrete molecular particle, and it occurs when two non-metallic elements combine. In reality, most things don't fit so neatly into two opposing boxes. It's pretty unusual to find a material where the bond is completely ionic or perfectly covalent. Most bonds lie somewhere in between these two extremes. Polar covalent bonds are bonds where the electrons are shared, but they aren't shared equally. They're more strongly attracted to one of the two atoms. That will also result on some charges on those two atoms, but they aren't as large as the full positive or negative charges on genuine cations and anions. This is a form of bonding intermediate between ionic and covalent, and it has benefits of both. Attraction of negative electrons to multiple positive nuclei, like a covalent bond, but also attraction of the opposite partial charges on either atom, which we represent with the lowercase Greek letter delta. This form of bonding is commonly found in compounds of nonmetallic elements, but now the elements must be different. Now let's practice classifying these three types of bonds. You might find a periodic table to be helpful. Which type of bond do you expect to find in the following three compounds? Silicon tetrachloride, difluorine, and sodium oxide. Not quite. Remember that a genuine ionic interaction requires the combination of a metal on the left side of the periodic table with a nonmetal on the right. Not quite. Remember that a polar covalent bond requires unequal electron sharing, so the two atoms joined by the bond must be different. I think you might have mixed up some of the definitions. Go back and look again at which combinations of atoms are required for each type of bond. That's right. Different nonmetals like silicon and chlorine will give polar covalent bonds. The same nonmetallic element, two fluorine atoms, will give a perfectly covalent bond, and a metal combined with a nonmetal like sodium and oxygen will give an ionic interaction. This intermediate case is called a polar covalent bond because charge separation causes an electrical dipole. In this case, the partial charges on the two atoms on opposite sides of the bond. Later in the course, we'll see how these individual bond dipoles can contribute to an overall polarity for the entire molecule. But how do we know which atom more strongly attracts the electrons? How do we know how large these partial charges will be? There's another property of atoms that we haven't discussed yet. That property is called electronegativity. It's kind of a big deal because electronegativity, more than any other atomic property, helps us understand how these atoms influence the properties and the behavior of the molecules they're in. Electronegativity is defined as the ability of an atom to attract shared electrons in a bond. We often designate electronegativity with the lowercase Greek letter chi. We can place each element on the periodic table on a numerical scale. The higher its electronegativity value, the more strongly it will attract electrons. So you compare the two electronegativity values for the two atoms in a bond. The electrons move more closely toward the higher value atom, so it becomes partially negative. That means the electrons move away from the lower value atom, and it becomes partially positive. You can easily look up these electronegativity values. They're in your textbook, on most periodic tables, they're on Wikipedia, and even Siri knows what they are. Hey Siri, what's the electronegativity of sulfur?
The electronegativity of sulfur is 2.58.
But really, you don't care about precise values for electronegativity. You just need to have a sense about which atom has the larger electronegativity. And there's a very simple trend. In fact, it's one we've already seen. As you move across a row, atoms get smaller and ionization energy increases because effective nuclear charge is increasing and the orbital energies drop. So it makes sense that as you move across the row, electrons are held more tightly and they'll be attracted more strongly. Electronegativity increases across the row. Down a column, atoms get larger and ionization energy decreases because the principal quantum number n is increasing and the orbital energies rise. So it makes sense that as you move down the column, electrons are held less tightly and they'll be attracted less strongly. Electronegativity decreases down a column. So as we move up and to the right across the periodic table, atoms get smaller, the ionization energy increases, and electronegativity values get higher. The most electronegative element is fluorine, with a value of about 4. One important exception to this trend is hydrogen. Despite its position on the periodic table, hydrogen has an electronegativity of about 2.2, which makes it close to carbon with a value of 2.5. For the purposes of electronegativity, imagine that hydrogen sits between boron and carbon on the periodic table. Now, let's see if this makes sense to you. Which atom has the highest electronegativity? Silicon, sulfur, tin, or tellurium? Consider the trend. The most electronegative elements are to the top right of the periodic table. That's right. Sulfur is the farthest to the top right of the table. With a higher Z effective than silicon and a lower principal quantum number than tellurium, sulfur is going to have the smallest atomic radius, the highest ionization energy, and hold on to its electrons the most strongly. Now here's the good bit. The farther apart on the periodic table two elements are, the greater their electronegativity difference will be. The greater the electronegativity difference, the more unequally they will share the electrons in a bond, and the larger the partial charges will become. This difference in electronegativity actually leads to a continuum of bond polarities, which you can see on this graph and in this table. On one axis, we have the electronegativity difference between two atoms. On the other, the percent ionic character of the bond, which tells you how polar the bond is and how large the atomic partial charges are going to be. When that difference is 0, because the two atoms are the same element, the bond has 0 ionic character. The electrons are shared equally, and there are no partial charges on the atoms. This is a perfectly covalent bond. when the electronegativity difference is very large, well above 2, say, then the bond has a very high ionic character. The electrons are almost completely or wholly transferred from one atom to the other, creating full or nearly full positive and negative charges. This is an ionic bond. In between, when the electronegativity difference is intermediate, the bond is polar covalent. Depending on how great the electronegativity difference, the ionic character might be quite small or quite large. The inequality of electron sharing can be low or very significant, and the magnitude of the resulting partial charges can be rather small or quite big. So, as the electronegativity difference between the two atoms increases, the bond polarity increases, the percent ionic character increases, the partial charges on those two atoms increases, and the nature of the bond moves through a continuum from perfectly covalent through increasingly polar covalent to ionic. So let's see if you can relate these ideas. You're probably going to need a periodic table for this question. Electronegativity relates unequal sharing of electrons to partial charge separation in polar covalent bonds. So, which bond places the largest delta positive charge on a phosphorus atom? A phosphorus hydrogen bond? A phosphorus fluorine bond? A phosphorus chlorine bond? A phosphorus bromine bond? A phosphorus aluminum bond? The electronegativity of hydrogen is consistent with a position partway between boron and carbon on the periodic table. If you were to look up the values, its electronegativity is almost identical to that of phosphorus. Phosphorus hydrogen bonds are essentially nonpolar. Not quite. To put the largest possible delta positive charge on the phosphorus, we need the largest possible delta minus charge on the other atom. That requires the highest electronegativity. Aluminum phosphorus bonds will be quite polar, and there will be large partial charges in that interaction. But remember, we want the partial positive charge on the phosphorus. That means it needs to combine with an element that has a higher electronegativity. Remember the electronegativity trend. Exactly. The size of the partial charges will increase as the difference in electronegativity increases. To put a large delta plus on phosphorus, I need a large delta minus on the other atom. That other atom needs the highest electronegativity we can find. That's fluorine at the top right of the periodic table. So, today we saw that chemical bonds form because atoms that are in chemical bonds are lower energy than atoms that aren't. Whether electrons are transferred to create an ionic interaction between particles of opposite charge, or whether the electrons are shared to create a covalent interaction where the electrons are attracted to multiple positive nuclei, chemical bond formation is always a downhill process. That means an input of energy is required to break those bonds. We learned that most chemical bonds lie on a continuum between completely ionic and perfectly covalent. Polar covalent bonds have aspects of both. The electrons are shared, like in a covalent bond, but they're shared unequally, which leads to partial charges and some ionic character. Finally, we learned about electronegativity, a property that describes the ability of an atom to attract electrons to itself in a shared bond. The more electronegative elements will be the farther to the top right of the periodic table. The greater the electronegativity difference between two atoms, the more unequal the electron sharing, and the higher the bond polarity and partial charges on the atoms. In your next class, you'll have the chance to explore these ideas about bond polarity and about electronegativity a little bit further, and you'll learn about some ways that we can represent the different types of bonds in different molecules.